just to recall what we have discussed in the last class, we have discussed some basic knowledge of real analysis, which will be used, and then we have discussed the definition of sequence. We have seen one example that how the convergence, a sequence xn n equals to 1 to infinity, it converges to x, a limit. What is the meaning? Okay, and then we have seen the quasi-sequence. A real quasi-sequence is always convergent. Then we have seen also the boundedness of a sequence. Then continuity of a function. That function, a function is, in simple words, a function is continuous if we can draw the graph of this function without lifting the pen. If I lift it, then it is not a continuous anymore. So for differentiability, that we have discussed already, and for multivariable case, we will take the partial differentiations and we will take the gradient vector. So this is gradient vector at a point x we will define. And we have also seen the directional derivative. What does it means? So gradient and directional derivative, they are very closely related to each other. And then twice differentiable functions, we have seen a function is called twice differentiable or C2 function if the second derivative is continuous and they exist. Similarly, the Hessian matrix is actually, it contains the Hessian matrix at a point that the symmetric matrix, it is having del f del x 1 del f del 2f, sorry, second derivatives, second order partial derivatives, and then del 2f del x1 del x2 del 2f for 2 by 2 for two variable case. This is a Hessian matrix, second order. This is a real symmetric matrix if we are considering about the real functions. And then we have seen also the second derivative, second directional derivatives, and then it was actually having the given a direction d transpose, we will apply this multiplication Hessian matrix and then d. Okay, so directional derivative was the dot product of the gradient vector and a particular vector given the d vector. And Taylor series, actually it talks about the Taylor series expansion, and then truncated Taylor series, they are basically applied for approximations. If we want to approximate a function, then we will take the help of this Taylor series. Then we have also seen the second order Taylor series truncated version. And finally, we have seen some that there are two types of direct proof and indirect proof of proof by contradiction theorems, and also mentioned the mathematical induction to prove any claim. So if we just try to solve these problems, for example, this is 1 and 2, then what are the things that we have to know? Whether it should give you a minimum value or maximum value, and what would be the solution. So it talks about design a rectangular box, open at the top will be open, to have the volume is 32 cc. So V is 32 cc. That is the limit is given. That is a resource constraint is given. There is a need. So we have to draw a box. And the top will be open. So you have to find the dimensions of the box requiring least material for the construction, for its construction. So that means here what we are going to optimize, the material optimization. We should not waste our resource. Okay, so for that case we have to design length, breadth and height. What should be the price? We have to design it. Now if we, and we know that volume is actually the product of these three things, length, breadth and height. So how we should be, what should be the combination to make it 32? Because 32 can be 2 2, so 3 times, it can be 8, 2 times 2 times 8. It can also be like 2 times 4, again 4. Yeah. So it can also be 1 times 2 times 16. So there are so many possibilities. But you have to design in a optimal design. We need to design the optimal quantity for which it will satisfy our requirements. Similarly, if we have a 2 variable function, then how to find the extreme values? Okay. So from calculus, we know that we'll try to find out. So if this is a single variable case, then we have seen that. For example, if this is example, we'll try to find out the derivative. We'll make it 0, and then we'll try to find out the double derivative, second derivative. We'll check whether it is greater than 0 or less than 0. So this is actually our plus 2 level knowledge that we have. But these are actually not applicable here. So for that we have to upgrade ourselves. Okay. So that's the motivation for today's class. Okay. And then to find the global minimum, we'll try to discuss the one-dimensional optimization. The function will be for one variable function. If we think about a multi-variable function, then okay, we'll talk about the single variable and multi-variable together one by one. And then let x is a n-dimensional subspace. Then function f is a, for example, this actually having f of x1, x2, xn. This should be some value, some r. R can be combination of summation of ci, xi. It can be ci into ci square, xi square, xj square, cj square, xj square. It can be like this also. So this r. Note that the resultant is a real number. Okay. Now we have to consider the optimization problem of this form. Okay. So we call it a global minimum. X star is a global minimum if it satisfies this relation, except for all x from this x, capital X set, all other points are actually the functional value. Functional value at x star is always less than all other values from the other x values. Okay. Now, if we just put x equals to r, that is the resource is unlimited because r is minus infinity to infinity, real number set. Okay, so this way, this is infinity plus infinity, and this way, this is minus infinity. This is real number set if you think about 0 and then. So this problem becomes unconstrained. Okay. Now, why this constraint and unconstrained are important, we will see soon. The question is, under what conditions f and x does the function attain its maximum or minimum or both. So if we have a simple function like this, then we can find an x star which will be a global minimum on this interval. We can find it by graphical method. But if we have a complex nonlinear function, this is also nonlinear, but it is a complex function, complicated. It has so many peaks. These are the peaks. These are the valleys. Now, we can actually define the global maximum point also. Just like we have defined that minimum point. So similarly, if we are talking about global maximum, then f of x star will be called global maximum point if we have this relation for all x belongs to capital X. Okay. Okay, right. Now there is a function f of x equals to, we have mentioned already, but let us revisit this problem again. F of x equals to x cube. So this is here, f is a function from R to R. Let us write x is a subset of R. So let us one variable function. Then at this origin, because if you want to apply this function f test of x, the first derivative is 3x square. How about second derivative? Second derivative will be 6x. Now if you try to find out f of 0 will be 0. It is neither greater than 0 or nor less than 0 nor greater than 0. So we cannot conclude anything. Like we have discussed when we have discussed the saddle point, so that there we have mentioned this problem. But the thing is, yeah, for maximization problem or minimum problem for a minima. So if you think about this around 0, so this is our 0 point, for example epsilon, and this is negative epsilon. Okay. So if we think about this, and the function is actually passing like this way. It is a continuous function. So if you think about this interval is minus epsilon to plus epsilon. Okay. Now if you think about this way in this direction, so it will become negative epsilon cube, so less than 0. But if you think about this epsilon plus epsilon here, so it will become positive. So sometimes it is positive, sometimes it is negative. So this relation does not hold. That means if you think about this relation, yeah, for all it will satisfy this relation. Then only you can tell that this is x star is a minimum point. Minimum point if it satisfies only one inequality. But here we can see that this is sometimes greater than 0, sometimes less than 0. So this is not a extremum point or not a local minima, neither minima nor maximum. Okay. The reason is happening here because we have considered the whole set. The main reason is x is not a closed, x is closed. This real number set is a closed set, but not compact. You remember a closed set which is bounded also, then we call it compact set. So is it enough that if we have a compact set, then we can get a that maximum or minimum point? So that is also not possible. So here it is. If you think about this, x equals to this open interval AB, then f and the function is f of x equals to x. So this is a straight line. We are thinking about only this interval. Okay. If you remember the definition of a supremum and infimum, then you will see that A is our supremum. Sorry, infimum point is A, and the supremum point will be the B. That means we'll take the upper bounds and take the minimum. So that will be least upper bound, that is B, that is called supremum. And infimum will be take the lower bounds, take the maximum. So that will be called infimum. Okay. It can attain this supremum and infimum, but this particular function, because this set is actually set of all those x for which A is strictly less than x and x is strictly less than b. Remember, these two elements are not included. That means if the set is not closed, since this is open interval, if this was the set, then we can claim that it has maximum and minimum, and they will happen here, this point. So this closeness is also important. The set is bounded. Remember, the bounds are actually A and B. The set is bounded, but it is not closed. So boundedness and closeness is very important in order to become the compact. Since this is not a compact set, so we can have, so here this minimum and maximum do not occur here. Okay. So now if we think about the closed interval A minus 1 to 1, and if we define the function of this form, so at minus 1 to 1, it will become of this form x. Otherwise, at x equals to 1, it is 0, and x equals to minus 1, it is minus, it is also 0 again. So this function is not a continuous function, because at this point, after this point, it's coming to here, after this. So not continuous function. But the set is compact. Now the set is compact. Yeah, even after having the compact set, we are not able to get the maximum or the minimum. Maximum or minimum. So this is closed and bounded, so x is constant. But f is not constant on the whole interval. It is continuous up to from here to there, except these 2 points, this plus 1 and minus 1, except these 2 points, the function is continuous. So in other words, this is not a continuous on the whole set. So continuity is also important, not only compactness. So continuity is also important. These two are important. So this leads us to the next theorem, which says the compactness. So it is continuity or compactness. They alone cannot guarantee the maximum or minimum. Now, if you remember, for our school level mathematics, we do not think about compactness, continuity. Given a function, we directly go to differentiate and we'll make it 0, find out the point, and then check whether it is there. But that techniques are not will be suitable for here now, because we have to verify. This is regarding the existence of the solution of a optimization problem. If you remember, I have mentioned somewhere in the, I think in the second lecture, that we should talk about the existence of a So this was the case that we have. So 5 steps. So that 5 steps, according to the 5 steps, checking the existence of a solution. We have discussed this one. I said that we will discuss somewhere. So today's lecture is actually based on to find out the existence of a solution. There is a maximum or minimum. Okay. Okay. So this is Weierstrass theorem, is very important theorem actually. It says for a given subset of Rn, be any non-empty compact set. Remember, we are talking about compact set. And F is continuous on X. On X means that is the domain overall. Okay, all the points of X, it is continuous. If you remember, here the it is not continuous on the n points, -1, 1. So if we have such situation, these are the conditions. Then if these two conditions are satisfied, then F attains a maximum and a minimum on the set X. That is, there will exist 2 points, say x1 and x2, for which x1 and x2, and they both of them will belong to the set X, for which we will have this relation. One will be maximum point, another will be minimum point. For all X belongs to the capital X. Note that this actually Weierstrass theorem provides only a sufficient condition. Sufficient conditions for the existence of a optimal. It does not give any necessary condition. Now there is a two type of conditions. One is sufficient condition, another is necessary conditions. Okay. Now if you try to understand what are those things actually, what are necessary conditions and what are sufficient conditions. In simple words, I have mentioned once that if you want to write this 12th class exam, 12th class board exam, then it is necessary that you have to pass the 10th class board exam. But suppose someone has passed this 12th class, then it is sufficient. This information is sufficient to tell that the person has already passed the 10th. But if you want to appear the 10th board, I mean, 12th board class exam, then it is necessary to pass this 10th board exam. So this, in simple words, it can be understood in this way. So there are some conditions which are sufficient. There are conditions which are necessary. Okay. Now here the Weierstrass theorem is not satisfied for this particular problem. If we have a discontinuous function, okay, though the exact form is not given here, but we can construct such function that it will follow this path actually. But that interval, this A and B, this interval, within this interval, the minimum point will occur here. But what Weierstrass theorem says? Weierstrass theorem says that if we have a compact set, here AB is compact, close interval AB, it is compact, and F is discontinuous. Here this function is discontinuous, but still we can find the minimum value. So this Weierstrass theorem is not necessary. So it does not give any necessary condition. And if we think about another example, if we think about the whole set, whole real number set, you can go to plus infinity, you can go to minus infinity. If you go there, then the function will approach to infinity. In the both directions, it will approach to infinity. But here at this point, it is having one minimum point. Although we have said that this R is not compact. Then also we can find the minimum. For example, if you define x minus 2 whole square f of x, then at x equals to 2, it will become 0 here. So this is a parabolic equation. So this will be our minimum point. But our set is not compact. So that is why this is only a sufficient condition, that if this is satisfied, if these two properties are satisfied, then it will definitely attain its minimum and maximum. But there are functions which do not satisfy these two criteria, but still they have minimum point. Okay. Now, as I have mentioned it earlier also, that if we have a simple function, it is easy to find the global minimum. But if we have several peaks and valleys, several valley, these are the valleys, and these are peaks. So it is really difficult to find out the global maximum or minimum. Okay. Now this will be our actually main target. So we will be trying to find out the local minimum. So this will lead us to define the global minimum point. Okay. So if you consider one constrained optimization problem, minimize fx subject to the constraint, x belongs to the capital X, x is the resource constraint. Okay. And then we define the global minimum point for this point. I think we have mentioned already. Yeah. the global minimum of f over the x is actually defined in this form. Okay. Since global minimum is very difficult to find or characterized for a general nonlinear programming problem, then should we stop? If it is difficult, shall we stop it? Okay, now the answer is actually we should try to make something happen. There is a saying, something is better than nothing. So that is why we should not stop. We must solve some of the problems. So that is why we have introduced the idea of local minimum. Now, if you try to relate this local idea of local minimum and the local maximum, let me just so how you can relate this local maximum and local minimum. You may be wondering that how it is related. I will tell the idea. So for that again I will take that example. Okay. So if you remember this example, as a product designer or product manufacturer, smartphone manufacturer, your local solutions are those you are actually dividing. This is your x axis and y axis. So up to this range, for example, this is 5,000 to 9,000, and then here after this is 10,000 to maybe 15,000. Okay, so how many customers are there? Okay, you have to find this number, and after these numbers, so you will get this value. So you will find the pattern of the purchase of those customers. So in this region, how much sale is there? So how much profit you are getting there? So similarly for this particular interval, so you are getting this local maxima or minimum. I would say this is extremum. Okay, so after collecting all the points, all the extremum points, so we can find the global maximum. So here it is. We'll try to find out the function here. Okay, we'll try to find all the local minimum, and then we'll compare them. Based on that, we will try to find the global. So for local minimum, what we do is, let us define the local minimum. X star is said to be a local minimum if there is a delta greater than 0 such that f of x star is less than or equal to all the functional value for x such that x belongs to the set x, and it is also belonging to the neighborhood. The B, there is you can call it a ball centered at x1, centered at x star, and of radius delta. This is a ball centered at x star and radius r, of radius delta. So this is our x. X we have said center. For example, this is whole space is our x. Okay, we are talking about n dimension. let us visualize on one dimension. So this whole line is our x. Now if you draw here, so the ball in a real one dimensional space is actually the intervals. So that means this is nothing but x star minus delta and x star plus delta. The meaning of this ball is here it is, the open interval. So in this interval, take any point, any x, this x star value will be minimum. F of x star will be minimum. We are not bothered about these points now. We are only focusing on the local. Now what is a strict local minima? So x star belongs to capital X is said to be strictly local minima, a strict local minimum, if this property holds. Here equality is not there. Okay, it is strictly less than, and the definition is same. Also remember, this x is not equal to the x star, all other points. But here we can see one a special function for which all the points that are actually they have the same value, but all the points that we are actually these functional values f of x, these are f of x values, they are actually all these points actually maximum points. All these points are at maximum points. This function is going to negative infinity. This is also negative infinity as x tends to as we increase the value of x, so it will become so this negative infinity. Here also in this direction it also goes to negative infinity. But this local maxima or local minima is not there. Okay. Around this place, okay, if this was a strict, then for you can find x1 and x2 here, for which f of x1 and f of x2 you can get them equal. There are many infinitely many numbers, infinitely many points are there for which we'll have the global extremum. Here it is maximum. So this relation should hold about this the interval. There is a ball centered at x star of radius delta. But in this case, we can see that these two are actually equal. So this is not a strict local maximum. So this global maximum, I mean the global maxima or local maxima, they are not unique. We can find multiple maximum. So when it is unique, we call it maximum or minimum. But if more than one optimal, okay, so not unique. When the optimal point I mean that sorry, not unique, we use the word maxima to introduce, I mean to indicate there are maximal or minimal plural sense. Okay. Yeah, for this this will come again and again. because our goal is to find the local minima actually. So we may have a situation that there are strict local minima. These are strict local minimum. This is global minimum after comparing. But this is, we have here is a weak local minimum. This for weak local minima, it will be like less f of x star. It will satisfy this relation less than or equal to. Okay, in this interval, it will satisfy this. So for weak local minima, we will have this kind of situation. But for the strict, we will have a strict less than. Okay. Now, as I mentioned, I think I have mentioned this thing that it may look that we divide this total interval into some sub intervals, and then we collect all the local points, local minimum points. After that, we compare them to get the global minimum. But this is also not applicable always. There will be some functions for which it may not guarantee the global minimum. There are kind of some complicated functions will be there. Okay. Now, if you think about this is a simple function, it goes to minus infinity, here also minus infinity, but it will have a unique minimum point. Minimum point is here. Okay, the function does not have a global minimum. It will have only local in this. That is why this comment is there that finding the local minima does not guarantee a global minima. So for this function, we do not have any global because it will be negative infinity. So minimum point is here. Okay, you may be wondering that if the functional value is negative, then this should be the minimum point, right? But that is not, because in real situation we cannot have negative infinity. What we will talk about only finite values. We should not talk about the infinite. I mean, a person cannot have any infinite loss, or a person cannot have infinite profit. So these two are actually, in order to keep that realistic, keep the things realistic, so this local minima will be considered for finite values. So similarly, that global minimum and local minimum. Every global minimum is also a local minimum. Yeah, that's true. So this is also, if you think about this one, this is a global minimum. But if you think about this interval, this particular interval, in this interval, it is a local minimum. Yeah, it is not possible always to identify the global minimum by finding all the local minimum. Because here we have seen, here only one local minimum is there, but there is no global minimum. So one has to check whether the function has a proper form. Okay? So that collecting all the local minima can give us the global minimum. Okay. So there are actually types of optimization problems that we have discussed. One is constraint optimization, another is unconstrained optimization. Unconstrained means we will not impose this condition. That means we will allow x equals to Rn or x equals to R, that you can take any value. So you can think that if this is not a realistic situation, then why we are studying? Because in order to solve these problems, These are realistic problems. For real problems are will be constraint problems. Okay. In order to solve them, we need the knowledge of unconstrained optimization. So this will be used here. So that is why we first understand the notions of unconstrained optimization. And then also again, we may have for unconstrained optimization, this one was multivariable case. This is also multivariable case. But in order to understand this multivariable, we need to understand the single variable case also. When f is R2R. So that means we will first actually, this is a groundwork actually. If you think this is a groundwork, then this may be treated as a first floor and then this is a second floor. So we will focus on the groundwork actually. Okay. So for unconstrained on-dimension optimization problems, here we are not worried about the x. We are not worried about. So this is a given. We have the freedom to move from minus infinity to infinity. Okay. So that is why we have written. So we have to idea of this 3 will be used in 2 and the idea of 2 will be used in 1. This would be the circle. This would be the structure. So we are focusing now this one. So what are the necessary and sufficient conditions for a local minimum? After this, any doubt?
Sir?
Yes, tell me.
Sir, is there any optimization problem that works with complex variables?
Complex variable optimization.
Yes, sir.
I think there is, I mean, we can use complex variable optimization techniques. Okay. Yes, I think we can do that. We can apply because the idea of complex analysis are used in several fields. But I mean, if you want to solve any real problem, okay,
Yes, sir.
that the complex variable, for example, if you want to, this is actually, if you remember the complex variable, this is 1, this is x-axis, and for complex variable, this is y-axis,
Right.
1 plus I. So what will be the meaning of I? I will be root over minus 1. So if you think, if you say your resource 1, your one variable is this part, okay, this one, x1.
Okay.
So resource 1, so it will not indicate any kind of real situation.
Yes, sir.
So that is why we mainly focus on, for optimization techniques, we mainly focus on this real variable case.
Okay, sir.
Okay. But yes, of course, this application of complex analysis, there are several applications are there. I am not able to give you some particular example right now, but I can recommend some textbook where you can find.
Okay, sir.
Okay. So yeah, let us understand the necessary condition or more carefully. Necessary conditions are those which are satisfied by every minimum, every local minimum. Okay. Let me tell this local minimum. And the sufficient conditions are those for which will guarantee a local minimum will exist. Okay. So how to characterize the local minimum? Is there a good approach? I mean, the approach will be good, or there will be task will be easy if we have a simple functions like this, or if we have a function like this. If the function is smooth type of function, but if the function is this kind of function, not so smooth, having multiple peaks, and so then the task is not so easy. So we need to understand the first order. What is the first order necessary conditions? So for this, we need to assume, these are the assumptions, okay, and consider the problem or unconstrained problem. This is one variable case we are studying now. This means that f dash exists. Okay, if f belongs to C1 means f dash exists. The first derivative exists and continuous. I'll say continuous, CTS, continuous. Okay. Then the theorem says if x star is a local minima of f, then f dash x star is equals to 0. So we have studied in childhood also, from school mathematics also. So, but only thing we have not mentioned this thing. Yeah, this is a necessary condition. So proof is actually very easy, proof by contradiction. So I'll leave it to you. Just try to follow the proof. I'll skip the proof here. If you do not understand, please ask in the next class. I will explain. So the meaning of it, if, okay, the meaning, let us understand the meaning of theorem 1. That is first order necessary condition is, if we have a function like this, then if say the function, it says if it is a local minimum, then it must satisfy this, then it will satisfy this. So in order to finding the problem, so what we do is we will try to find out the derivative, and if we, whether this function, if we make it 0, then we will find out that x equals to 2. And we will try to find out if dash x equals to 2. If we substitute 2 here, so 2 minus 2 is 0. So that means this is our, okay, by this theorem 1, this is our actually first order necessary condition. This is our minimum point. X equals to 2 is a minimum point. Okay. And if we think about this problem, fx equals to x square, then we can see that f dash of 0 is equals to 0. So x equals to 0 is also a local optimum point. Here it is maximum point. But the slope is actually is 0. That means the tangent will be parallel to the x-axis. The tangent at that point will be parallel to the x-axis. But does it say anything more? Whether it will have a minimum point or a maximum point? Actually, it does not say anything much. It does not talk about the curvature. So f dash x 0, okay, f dash of 2 is 0 for this case, and f dash of 0 is equals to 0. But it is not talking about whether it is the curvature, whether it is this curve of this form or it is of this form. It is not talking about the curvature. So looking at the slope, we cannot, it does not tell about the whether we have maximum point or minimum point. This telling about we have a local optimum Whether maximum or minimum, it does not tell. So for that, we need to see some more example. For if you think about this problem, whether it is a optimal point, or here also, if you think about this derivative, so derivative will be f dash x equals to 3x square. So f of 0 equals to 0 here also. So derivative is 0. It can happen for so many cases. But the point that we are talking about, that particular point x, whether it is a saddle point or it is a maximum point or minimum point, it cannot tell. It just says only a necessary condition. Okay. If you want to understand, if you want to find the optimum point, extremum point, for that we have the derivative is 0, the first order necessary condition. It can also happen saddle point. So this stationary point where f dash x is equals to 0. So this will be giving you the values of x1. After solving this equation, we can find x1 values. And these stationary points can be divided into two parts, bifurcated. We can bifurcate as a saddle point, neither maximum nor minimum. And this optimum point can be treated as, or extremum, we can call it extremum, saddle point and extremum, optimal point. So either it will be minimum or it will be maximum. So for this, we have to understand some more extra conditions. So what are those conditions? So let us see. Okay. Now stationary point, as we have mentioned, by definition, it is derivative will be 0. So f dash x equals to 0 is a necessary condition for local minimum, but it is not a sufficient condition for this local minimum. So how to ensure that the stationary point, that particular stationary point, is a local minimum point? Okay. How to rule out this case? How to rule out this case? So for that, we need second order necessary condition. So the second order necessary condition tells that if, let me state the first theorem. Assume f is a the function real number to real number set, one variable case, and f is C2 function. That means that f double dashed is continuous. Remember, for the first order necessary condition, we have considered only this first derivative. We have not talked about the f2. So for that, we need some extra conditions. Extra condition is that we have to think about this should be a second derivative function. Second derivative must be continuous. And also, then the x star will be called a local minimum if f is 0, f dash of x is 0, and the second derivative will be greater or equals to 0. If you find this variable, so this is f dash x. So f dash of 2, x equals to 2. Here x star is actually 2, and here x star, let us assume x star equals to 0. X star is 2. So first derivative is 0, so that is satisfied. So second derivative is greater than 0. So whether if it is greater or equals to 0, then it is satisfied. Okay. So now we can call it a local minimum. So similarly, if it is, so first derivative is 0, but the second derivative is less than 0. So for this we can call it a local maximum. If it is greater than equals to 0, then it is minimum, and if it is less than equals to 0, then it is maximum. So this is all about the second order necessary condition. Again, I will leave this proof as an exercise and try to prove by contradiction. Proofs are actually, I would like to skip them just for, I will explain the meaning of the theorem. Okay. Now the question is whether they are sufficient conditions. Second order necessary conditions, can they alone guarantee the local optimal? The answer again will be no. For this, the same example we can talk about. If you think about this second derivative, second order derivative, so this is 6x, but f of 0 is equals to 0. But this is not a neither minimum nor maximum. So this is a saddle point. So these are not sufficient condition. These are only necessary conditions. I mean, it is like writing the 10th board exam or applying for any job does not guarantee that I will pass the exam or I will qualify the interview. Okay. Those are the necessary conditions that in order to qualify or in order to appear for the interview, I need some qualifications. So this necessary conditions. So you can understand this necessary condition in this perspective, in this way also. So now we want to explain the sufficient conditions. So what are the sufficient conditions that will give you the guarantee? So for this, after satisfying the necessary conditions, if you, for example, this interview problem, okay, if you perform the interview good, or if you perform the exam very good, then there is a guarantee that you will be selected or you will get a good mark or pass mark, at least you will get. So in order to guarantee that there is a local optimum, so for that we have to state the theorem. So this theorem says if x star is such that this is 0, the first derivative is 0 at this point, and also this is strictly greater than 0. It is not talking about 0, greater equals to 0. No, not that. It is strictly greater than 0, strictly positive. Okay, then it can say that this is then x star is a strict local minimum of f over the point R. Okay. So the second order conditions, they only guarantee a strict local minimum, but they are not necessary. Remember, they are not necessary. But if you think about this problem, this f of x equals to x to the power 4, then you will have f dash x equals to 4 into x cube. F double dash x, you will have a 12 x square. But if you think x star equals to 0, then f double dash x star, and both of them are actually 0. But still x star will be a local minimum for this function. So these are These are actually only sufficient condition. They are not necessary. The second order sufficient conditions. Now this is second sufficient optimality conditions. Now we have the necessary and sufficient conditions we have seen. So what will be the sufficient optimality conditions? Under which conditions we can find an optimal solution? That remember the existence of a solution. So here it is. So f is one variable function from real number to real number, and f is infinitely many times differentiable. All derivatives of f are continuous. Let us assume, also let us strike off the special case. It is not a constant function. For example, f of x equals to k or 2 is always a continuous function. It will have all type of derivatives. Okay, so let us not consider this case also. Okay, and then let the kth derivative of f at the point x be denoted by this function f to the power k in this form cos t, the kth derivative. Then consider the problem minimize over x belong to the R and fx. So then the sufficient optimality condition says, it says one theorem, by this theorem, let us call it 1 or 2. So x star is the local minimum if and only if. So this is a very strong theorem, strong tool. If and only if. So that means of this notation. If we assume this, we can prove this one, or if we assume this one, we can prove this one. So that is the meaning. So what it says, the first non-zero element of the sequence of the derivatives is positive and occurs at even positive k. What is that meaning? So if you think about f of k, so that means first derivative, this is second derivative, this is third derivative, this is fourth derivative, and so on. Okay, so the first non-zero element will be positive, and that will occur at the case of even numbers f2, f4, then f6 and f8 and so on. These odd numbers will not help to get the optimality. Only the even numbers will help. Okay. So for this one also, let us the same problem. Here it is local max minimum. Here it is talking about local max. Sorry, this is minimum and this is maximum. So f2, f4, f6 and f8 should be less than 0. The same theorem can be applied. Now, this is more powerful theorem which can guarantee the which can tackle the it can overcome the problems that we have seen earlier. Okay. Now it is to understand this function. So f dash x is 0. How? Because we have to find, if you make it the f dash x is 0, okay, try to find out the stationary points. Now, which point is minimum point, which one is maximum point, and which one is saddle point? We have to verify. Or whether all the points are actually minimum points. For example, if all these points are minimum point, then what will happen? A function will have of this form. So it will have, and then it will go down again for -1, again this type of, so -1, 0 and 1. So all 3 points are minimum points if possible. We don't know whether it is minimum or maximum, that we have to investigate. Okay, so let us investigate. So we note that f dash of 0 and f dash of +1, f dash of -1 equals to 0. So first order, this is first order necessary conditions. Okay, now we try to go for the second derivatives. So f dash x is this one, so we have found this one, and f double derivative f dash 2. So second derivative will be 12x minus 12x x square minus 4. Okay, now we observe that f dash of 0 equals to, so 12 into, sorry, this is double dash, f double dash, this is double dash, this is less than 0, so we can call it strictly less than 0. So this is a strictly local maximum, but for this point we can have, this is strictly greater than 0, so we can call it a strictly local minimum. Okay, and this one is strictly greater than 0, so this is also minimum. So the function will look like of this form. So 1 minus 1 is minimum, plus 1 it is also minimum. Okay, and 0 is actually maximum, so 0, so it will look like this form, or after that it will going like this. So initially what we have assumed here, that it will be look like this, so it is not correct. So it is actually of this form. Now if you think about another example, whether we can apply this theorem for this example or not, so we can say that this is x cube, x square minus 1 whole to the power cube. So try to find out f dash x, and then try to verify the stationary points. So here the stationary points are 0, plus 1 and minus 1. Okay, these are the stationary points. Okay, right. Now we try to find out f dash x is 0. So first order necessary conditions are satisfied. Then we have to find out the second order necessary conditions, whether they satisfy. So in that case, we have to differentiate again, and we try to find out the differentiation. So the second derivative will become of this form. So 30 into 0. So this function is strictly greater than 0. So if it is greater than 0, we can call it a minimum point. But here these functions are actually equal to 0. So nothing can be concluded based on this information. So we need higher order derivatives. So let us compute them. So for higher order derivatives, the third order derivatives we have calculated, and we can see that if this higher order derivative is actually, one is positive and another is negative. But these are actually saddle points, because we cannot say about the corresponding to 1 and -1, the sequence. Remember the sequence? F1, F1x, F2x, F3x, and F4x, and so on. The sequence of derivatives. The sequence of derivative, first derivative should be, first non-zero should be like F2 or F4 or F6. But here what we are saying, F3 is actually non-zero. So this is not a local minimum nor a local maximum. So this is a clear-cut case of saddle point, because 3 is not an even number. Okay. So that is why we cannot talk about the local, strict local minima or maximum here. So if you think about this problem, x to the power 4. So for this problem, we can talk about that. We'll think about this third order derivative. It is 0. Second order derivative, it is also 0. First order derivative is also 0. So this is first order necessary condition. Okay. But second order are actually this is also 0. This is satisfied. This is also 0. So this is also satisfied. But the fourth order, it is the greater than 0. So the first non-zero element is actually in the fourth derivative. So it is happening for one even number. So 4 is an even number. So that is why we can claim that this is the local minimum. Okay. So if you just want to summarize all the cases. So first, the derivative of the function. We want to need, then we identify the stationary points. Third, we need to find the higher derivatives and check for which particular key, whether k is even or odd. Depending on that, we can conclude. And also we have to verify the candidates. We have to verify if we can conclude about the stationary points of the local minima and maxima. So these are a few observations. Now the thing is, if this calculus can give us the solutions, okay, then why do we need some algorithms? I need another 5 to 10 minutes, so please not that much. So this only one concept that we have left out, so that is the need of algorithms. So for this problem, finding this minimum problem for this problem, finding the minimum point of this problem is not a simple. It is simple. We don't need any algorithm. But if we try to find out the solution of this problem, so this is not going to be 0. E power x is never 0 for all x. So how do you, and if you derivative, if you differentiate f dash d dx of x, it will give you the e power x only. So for a simple function, it is not even that much complicated. For a simple function, we are not able to find the exact solution by this calculus method. So for this reason, we need the numerical techniques, which will actually give us, for first iteration, the solution is Tn, T1. Then second iteration T2, and then third iteration T3, and then n iterations. Okay, we'll get a sequence of solutions which will actually converge to the ideal solution. The aim of this this numerical techniques is to So if you try to make this as sequential point of view, an and a, that should be less than epsilon greater than 0. It can be like 0.01. That means our actual solution and our obtained solution, the difference between these two will be very, very less. So that is the main motivation of the this algorithmic approach, numerical approach. So if you have any doubt, you can ask me.
Sir,
Yes, tell me.
sir, is the set of real numbers compact or not, sir?
Set of real numbers is not compact. It
So
has to
then
be
who are-
bounded.
Yes, sir. Sir, then how are we using it for one-dimensional optimization, sir?
How are we? How are we going to use?
Yes, sir.
Actually,
Sir,
for your question is not clear. Can you repeat?
Sir, we already saw that if the resource set is not compact, we cannot use it for optimization.
Okay.
Since the set of real numbers is not compact, then
Okay.
how are you able to find the optimum for the function fx equals x squared or x power 4 something, sir?
Yes, yes. Just now we have said no. See, the compact set will actually, it has to be, say, this theorem actually, where I have mentioned, yeah, here. These are actually necessary conditions. Compactness is a necessary condition. See here, it is not a compact. X is not a compact because it is not bounded. Bounded set means, well, what is a bounded set? S is bounded if S is a bounded set if for all x we can get a real number R such that all the x belongs to S. So all the elements of S set is actually less than some number. So in that case, we can say this is a bounded set. But real number set is actually this real number set
Yes, sir.
is actually minus infinity to infinity.
Yes, sir.
Okay, so this is unbounded set. We cannot find any number which will become again for this. We cannot get this. You cannot. Infinity is the maximum element. It is the maximum element. You cannot get any such real number which is more than infinity. Okay. So here this compact set X is not compact, but we are able to find the minimum. That is why I mentioned this. This is just a sufficient condition, like Weierstrass theorem. Yeah, if you remember this Weierstrass theorem. So it says if the set is compact, if the set is compact and the function is continuous, then we can get the maximum and minimum point. Okay. But this does not, it does not say that this is the only situation we can get. It is only saying that if you have these two conditions satisfied, okay, continuous and compact, then it will admit the minimum and maximum. But there are situations, they are not necessary conditions, remember? Okay, these are only sufficient condition. There are situations where it is not compact, but we can still find the minimum point.
Okay, understood, sir. I got messed up with all the dimension, all the definitions and theorems. That's right.
Yes, yes, yes. So these are actually, yeah. So you have to be careful about the claim because whenever you give, I mean, you are going to propose a solution to a problem that should be valid. Okay. So, I mean, go through all these documents, go through all these theorems and examples that I have discussed, and then try to solve the problem that I have mentioned at the beginning of this course, of this class actually. Try to solve these two problems. I have given the possible solutions. Okay. I would say, I will not say these are actual solution. I may be wrong. I mean, from where I have taken these examples, they may be wrong. So in that case, I will say verify. So it will take care of any mistake. So verify. If you get the same answer, then no problem. So if you get a different answer, then just inform that, sir, you have given some wrong information.
Okay, sir.
Okay, right. So these are your tasks. So in the next class, we will see the search techniques. How do we find the optimal point? So one-dimensional search techniques we will approach. Okay. So any more doubts?